Hello everyone. First to test, is my audio properly coming? Am I audible? If everyone could just post in the comment section if I am audible or not, it would really be great if anyone could just let me know if I'm audible or not in the comment section. Okay, so we'll wait for a couple of minutes before beginning this session. We'll let other folks join.
Am I audible?
Yes, you are.
Thank you.
Meanwhile, if you haven't subscribed to our channels, here are they. You can follow us on Facebook. You can follow us on Twitter. And also you can join our community in Telegram. So also, yes, if you haven't subscribed to our YouTube channel, please do. You'll get notified of latest videos that we publish. Uh, our monthly meetups often get recorded and we publish them as well in this YouTube channel. So yes, if you have any queries, you can also mail us at tfugcall@gmail.com. That's our official email ID.
I think people are joining in.
Yes, we have a lot of people now. And so I guess we are ready to begin. So welcome everyone. I am Rishiraj Acharya. I am the organizer of TensorFlow User Group Kolkata. And joining with me today is Ritwik Raha. He is a machine learning engineer at PyImage Search, and he is also a Google developer expert in machine learning. And this is the first of the many machine learning paper reading club sessions that we will be having. These are online only uh, theoretical paper reading sessions that uh, we'll have monthly. So to begin this session, we discussed which paper we can go through. And out of the many options we had, deep residual learning for image recognition seemed the obvious choice for us to go. With over 130,000 citations, it is very rare to come across any uh, neural network architecture where you would uh, not have contributions related to this paper in some way or the other. So I would invite Ritik Raha to take over and continue this session.
Great.
Meanwhile, you
Uh,
can also ask questions in the comment section. I will pick up those questions in intervals and request Ritik Raha to answer those.
right. So, Rishiraj, I would kindly request you to add my screen so that I can present. Yeah, great. Um, I had a slide ready for introducing myself and talking about all the great things that I've done, but Rishiraj summed it all up, so I won't be wasting any more time doing that, and I would dive straight into the topic. Two things about the topic. I think what Rishiraj has put out on the screen in bright orange is kindly read the paper before coming here. But I would like to, let all of you know that even if you have not read the paper or have not found the time to go through all of that, it's totally fine. You can ask questions over here. You can put them in the comments, and if they're relevant, if they're about the paper or about subsequent papers or related topics in the machine learning space, then Rishiraj will pick it up and he will pause me so that I can talk about it. That those are the two things that I would that I wanted to tell you beforehand. Also, some things that I want to share is that this is going to be a little more theoretical. We are not going to go line by line on the paper. Instead, we are going to be focusing on the core concept of the paper and trying to make it our own. So I know you don't hear this a lot, but if you have pen, paper, notebooks, iPads, whatever, anything to take notes on, anything that you need to kind of scribble and test your own theoretical understanding, I would like request you to do that, gather that. So, without further ado, let's get into the topic. Right. So, just a second. So let's wind the clocks back a few years and talk about ResNets. And yes, that's right. We are going to be talking about ResNets in 2023, and not about any fancy architecture or you know big models that you see around here, but a small experiment in the machine learning world that gave humongous returns. So the paper's name, as some of you might have gathered, is Deep Residual Learning for Image Recognition. It is a foundational paper in the deep learning community, and it introduced something called residual networks or ResNets. Now, about the abstract kind of sums up the paper, which is true for almost all papers. About the abstract, it goes like this. Normally, as you add more layers to a deep learning model, it should get better at its task because it can learn more and more complex features. Uh, this is not always true. In practice, deeper networks often don't perform as well as expected. So they can be harder to train due to something called vanishing and exploding gradient. If you like don't relate to that right now, don't worry. We'll come back to this later. So there are problems if you stack layers on top of each other, and that this paper was introduced to address this problem with a simple yet groundbreaking idea. So instead of trying to learn the function, which is like true for all deep learning models, they're trying to approximate or learn a function, underlying function. But instead of trying to learn an underlying function, the author suggested why not learn the difference or residual between the current layer and the desired layer's output. And this is done using something called a shortcut connection or skip connection that bypasses one or more layers. And how this is going to happen is what we are going to be talking about throughout this session. So imagine you're trying to solve a math problem. So instead of calculating the answer from scratch, you use a previous problem's answer and just figure out the difference between the old problem and the new problem. I'm sure most of us have done this. All of us being honest students, this difference or this gap between the old problem and the new problem is what the authors term as residual. And ResNets, which is like abbreviation of residual networks, use this residual connection to effectively skip layers, making it possible to train like really deep networks, like 152 layers deep. And at this time, you're probably wondering, like, hey, hold on, 152 layers deep isn't that deep at all. But I promise you, like when this paper came out, 152 layer deep, like making a network 152 layer deep and making it stable was a feat in itself. So like uh, that really resonated with the community. So of course, when tested, these ResNet architectures set new performance standards in image processing and image like recognition tasks, and from there onwards, like you will see later on this on in the stream as well, that ResNets or residual connections have been like really adopted by the community, and how like most great deep learning architectures actually use residual networks, and we'll see the reason in a while. But before that, let's try to understand the problem. The paper in question, it aims to ask a central question in terms of deep neural networks: is deeper always better? Which means if you stack layers on top of each other, is it always going to give you, more and more returns, or is it going to at some point be giving you diminishing returns? So, what I want you to do is think of training a deep neural network like trying to pass a whispered message in a game of telephone across a long line of friends. I'm sure most of us have done this in our childhood, where we, try to pass on a message and whisper it in the ears of our friends, and at the end, the last person who has heard the message relays the message back or shouts it out, and we see that like it's a completely different message, or it's a completely different phrase or a word. So to make it more interesting in this game of like whispered messages, the first person whispers a puzzle, and a group of progressively smarter friends tries to decode it. So every friend is smarter than the previous friend, and they are trying to decode or crack a puzzle which has been whispered uh, by the original person. Everyone with me till this point? Like, um, is everyone on the same page? If you are, please, like, if you are not, please put it in the comments. Okay, moving on. So um, the catch is, the more friends you add to the line, the harder it gets to keep the original message intact, because one, the friends are, of course you're whispering the message, so the message, some part of the message is getting lost in relaying, and again the message itself is a puzzle, so you have to kind of uh, decode the message while you're relaying it. So someone is saying explain it once more, so I'll go once again. What is happening is, you have a long line of friends, and in that long line of friends, the original person is whispering a message, and every one of those friends are relaying that message to the next person, right? And to make this more interesting, to make this game more interesting, the original message itself is a puzzle. So if like every other person has to decode that puzzle, and at the end the last person will be telling the answer, uh, or the key to the puzzle. But the catch is, the more number of friends you have, the harder it gets, because of course if you're whispering a message across a long line of people, the message itself will probably get lost, and then on top of that, the message itself is a puzzle. So every person has to decode that puzzle, and they are they are not being able to keep up. So it's like a telephone game, but it's harder. So this actually was an analogy for deep neural networks at that time. Like, you're adding layers, and those layers are trying to figure out the feature from the original image or the original message. And as you do that, the features are getting lost, right? So it's getting harder for the end layers or the last few layers to actually decode or understand something from the image. And this is why, like, the authors thought of this paper in the first place. So how do we solve that? So unfortunately, a game of telephone is, in this universe, still not considered a formal framework for doing deep learning. So we must once again resort to mathematics to understand this problem. So just bear with me. If you want to take notes, scribble something, that's fine. But listen to me first, and then do that. So capital F is the class of all functions together with weights and parameters. So what I mean by that is that, like, it's the class of all possible functions given a neural network. So a neural network or a deep neural network is supposed to approximate a function. We are saying that capital F is the class of all functions that are possible, uh, you know, uh, together with its weights and parameters, which means that for all functions small f, let me know if you can see the pointer on the screen, which means that for all functions small f, there exists a set of parameters which can be obtained through training. What this means is that, given a set of all possible functions, there must exist a single function f which you are trying to approximate, which you will be able to approximate given back propagation and training, right? So putting this into like a formal equation of sorts, f star, just a second, f star is the optimal function we want to approximate by finding the minimum possible loss from the data x and the labels y, provided that the function f belongs to a bigger class of functions, capital F. I know at this point you're like, just stop it. I cannot take all this maths anymore. But this is like really, really fundamental and really easy to understand once we break it down. So hold on. What I'm trying to tell you is that there exists data x and there exists labels for those subsequent data points y, right? And given these x and y labels, there must exist a function f star where the loss the loss for the neural network which is training on this data x and y is the lowest. Okay, and this is something that we all know at this point, doing deep learning or doing machine learning for some time. We have some data points, we have the labels to those data points, we have a neural network that is continuously finding out the loss while training on this data, and where that loss is the lowest, is the most minimal, is the actual uh, function that we are trying to approximate. Okay, I'm sure, like, this is not new knowledge to us, but again, if you don't understand this, or if you don't like if you find something amiss, please put it in the comments and we'll revisit it again. So this is what f star is, and uh, this is how we approximate a particular function given data x and labels y. But it can now be hypothesized that a more powerful class of functions f, and let us call this more powerful class of functions f bar. So f bar will be better at approximating f star. So think of it like this: you have a pool of all. So let's say you're taking a quiz, and like, you have a pool of possible answers while you are taking that quiz, right? And what is happening is that that pool of possible answers will have some other random answers as well. Not all of them uh, will be related to your quiz or your questions, the questions that you are attempting on the quiz. But when like when you say that, okay, I don't want this pool of answers is not exactly the best pool for me to select answers from while I'm taking the quiz. When you say that I want a better pool of answers which has all of the uh, answers to my quiz questions, or which has most of the answers to my quiz questions, you are actually trying to sample from a better class of answers, and that is what is happening here. So when we are saying that f star can be approximated given small f belongs to capital F, where capital F is a class of all functions, we can always say that, if there's a class of better functions, a class of more powerful uh, capital F, then f star will be better at approximating that. Is everyone with me at this point, or like, is it going everywhere? I'm going to give a couple of minutes for people to chime back here if they are at all here. But cool. So coming back to this analogy, it can be hypothesized that a more powerful class of functions, f bar, will be better at approximating f star. That's all we needed to know. So what we can do is, with training, we aim to find more and more powerful f bar that will eventually approximate the f star. So what is happening here is that, if you see on the screen, f star here is the function point, optimal function that we are trying to approximate. And what we are doing is we are creating progressively powerful class of functions. So f1 bar, f2 bar, all the way till f3, f4, fn. And we are trying to include f star, include this little point, just a second, this little point inside this class of functions. Okay, that's what we are trying to do. Okay, we are trying to approximate f star with a more powerful f bar. However, with f bar, like f4 bar or f3 bar or fn bar, not including the original f1 bar, like it's kind of overlapping, but it's not including the original class of functions at all. So there's always a possibility that fn bar will never approximate f star, right? Putting this into perspective, this is our optimal function. This is the function that the neural network should approximate. Okay, and we are trying to create pools of or classes of functions which will eventually include that optimal function, so that with training and back propagation, we will then find f star within that optimal function, within that class of functions, right? But what is happening is that we are creating progressively powerful class of functions. But so if I ask you, where is going to be f5 bar, you'll say something somewhere around here, right? And then f6 will be somewhere around here. And what is going to be happening is that it will drift further and further from approximating the optimal function, right? So what's the solution? How do we solve this? The solution is actually kind of simple. It is to nest the function classes as we go forward. So I told you about the pool of answers, right? What we can do with that pool of answers is say that the next pool of answers for our quiz question, which is going to be a better pool of answers, should include the first pool of answer. Okay, and then the next one should include these two. So that is what is happening here. We are saying that f2 bar, just a second, f2 bar should include f1 bar, and f3 should include both of these, and then f4 should include both of these, and you get the point. And what is happening here is that eventually, when we create f5 by nesting these function classes, we are going to have the optimal function within that function class, and then it can always be approximated with good training. So what we are the answer to our question is, how do we have better function classes that can approximate the optimal function, is we just create nested function classes. That way, the original function class that we start with, f1 bar, is already included in the subsequent function classes, and that means that the optimal function will eventually be approximated by a more powerful function class. So coming back to the game of telephone, because all this math is good, but we need to kind of understand it in perspective of the game of telephone. This means making sure that some of our friends in the string of friends occasionally hear the original puzzle. And that's what it means where you nest the function classes, because the subsequent layers which are going to approximate the function should have some form of the original data, or the original information passed to it, not the derived version, not the feature extracted version, the original version. Of course, if you have a game of telephone and you're whispering the message across a long string of friends, and then occasionally some of your friends are hearing the original message or the original puzzle. So at that moment they are like, okay, this person has actually heard it wrong, or has actually decoded a part of it but heard the rest of it wrong, because here is the original puzzle. So when I pass it on to the next person, i will uh, I will decode it a little better. So this is in essence what is what the solution looks like. So, in the context of the paper, they are suggesting that when training deep neural networks, instead of trying to learn a complex function directly, it's sometimes easier to learn the difference or residual between the input and the desired output. So, what they're saying is that instead of trying to approximate the function by adding more layers, what can be easier is if we try to understand this little part where we have like where where we have the input and the desired output. So the desired output is of course the extracted features, but the input is the original message or the original information. So if you try to learn the residual, that will make the function learn a lot better. That's what they are suggesting, and this is achieved using shortcut connections or skipping certain layers. And at this point you're like, you probably are being able to map this with a game of telephone that we saw a while ago. So what is happening here is that there's a network here which has wet layers and ReLU and then a wet layer. What is happening here is that uh, the original information X is being passed back, skipping all these layers to another common point, and that this is called the residual block. Okay, and these connections help make the learning process easier without adding extra complexity. So just a second. So let's examine how the authors propose this solution, in deep learning terms, because all this while we know conceptually how it works, we know why it was proposed in the first place with function classes and everything. But let's examine how the authors propose the solution. Firstly, they propose the solution to be something called deep residual learning. So, what is residual learning in the first place? The original problem is to train a neural network to approximate a function hx. This can be difficult because of the reasons we saw, especially for deep neural networks. Deep residual learning this this part actually reformulates the problem by letting the neural network approximate a residual function. Okay, and that residual function, we can call it fx, is actually hx minus x. So at this point, hx equals fx plus x. uh, and if we want to understand in one word what is happening, we are trying to learn fx. What is fx? This small part. So I want each of you, like at least those of you who are listening to this or scribbling or trying to understand here, I want each of you to write in the comments, what do you think fx is? Given the diagram on the screen, it's practically written on the screen, but I want you to write on the comments, what do you think fx is? And if you don't understand it, just write the wrong answer, because like it will make me learn that I have to, you know, explain this again. I'm not being able to see the answers. So Rishiraj, I'll request you, if people are around here, can we put them, can we wake them up and ask them like this question?
Yes, please feel free to answer. They are there. I
Cool.
guess they are
Okay.
not
Okay.
able to answer yet.
Yeah. I'll try to like explain this in a better way. This is our original. This is our original, network. Okay, this is the original problem, and it is called hx. This entire block is called hx. Okay, what's in it? What is it doing? None of our concern now. This part, this part is called fx. Okay, and this point, at this point, the information there that is there at this point is, we can call it fx plus x, because this is the original x which is being added back at this point. So this is the new hx, which is called fx plus x, right? So if this is the, you're all saying answers which are true, which are defining what fx is, but I want you to write, mathematically, what is fx. Look at the screen, take a screenshot, try to see if you can write what fx is. Is fx equals x squared? If fx equals x, is fx equals hx minus x? So we have an answer. I In the interest of time, I will not wait for others, because you can revisit this as an exercise and understand it again. But yes, this is the right answer. I don't know what you get, pester Rishiraj for what you get, but you basically answered it right. Yes, again, fx equals hx minus x, and that is what we are trying to do. We are trying to understand. We are trying to model fx. We are trying, with our weights and parameters, with our learning algorithm, we are trying to learn fx. So fx is, as all of you are pointing at this point, hx minus x, right? And hx minus x is what? Is the information at this point minus the original information, right? So that is what we are trying to model. That is the residual which we are trying to approximate. Okay, and this is what the authors propose, that if you learn this residual, if you learn the, the the gap between the desired output and the input, then you will be able to learn, at a much faster rate than before. This is what the crux of the entire deep residual learning paper is. So just a second. but all is not well. There is something called the degradation problem, and the degradation problem is a phenomena where the training error of a deep neural network increases as the network becomes deeper. And we talked about this, at the beginning. If we add more layers to a deep neural network, will it always get better? Evidently not, because at some point it will not be able to extract features more meaningfully. And to understand that better, we had an analogy. If we add more friends to a long line of friends, just a second, I'll come back to your question. But if we add more friends to a long line of friends, will they always be able to uh, understand or decode the original message? Evidently not, because at some point they'll lose sight of what the original message is. So this is what the degradation problem is. Rishiraj, who is in the stream with me, is asking a question in the comments for some reason. What if the dimension of the output and the input is different? Like, if output is text and input is image, how do we subtract output from input to get residual? Rishiraj, question is good, but the answer goes something like this. Your residual block is not supposed to span an entire network. Like, it's not supposed to be like it's not supposed to start from the very beginning of the network and end at the very end. It should be somewhere in the middle, preferably between two or three layers. So, like, once you're inside a network, once you are inside these layers, you're either going to be working with one form of data, or even if you're working with two or three types of data, they are converted into tokens or embeddings or numericals, which the layers understand. It is not going to be in the form of an of text or image. But yeah, I'm coming back to that question. Can hx be zero? But again, um, what i what I kind of drew from your question is that, what if the shapes of, and this is a little bit more difficult for this introductory session, but I'll answer it anyway. What if the shapes of the output and the input is different? How does residual work in those cases? So the answer is, like, if the tensor shapes are different, if the array is of different dimensions, it is your prerogative to kind of squeeze or expand those arrays in a format that is kind of allowing this residual connection to happen. Okay, you cannot have a residual connection where your tensor dimensions are of different shapes. So I think that might in some form answer your question. Please let me know in the stream or in the comments if that does. uh,
Yes, it answers perfectly.
to Shubranil's question, uh, to Shubranil's question, uh, I'll not answer this directly, because if I answer this directly, where's the fun? Can HX be zero? Of course, in this case, you probably know the answer already, because HX cannot be zero because it is a network. It is a function. The value of HX is whether it can be zero or not is something that you want to understand. But I want you to go back and visit deep learning or machine learning from the first principles. What is machine learning? How is it happening? What are weights and biases? How are we approximating a function? Y equals mx plus wx plus b, where w is the weight and b is the biases. And of course, y equals wx plus b is one part of the problem. Then from there on, we are using activation functions. And activation functions, one of the reasons for using activation functions is so that the matrix multiplications, or the result of wx plus b is not negative, or not in a format that is unusable. So I want you to go back to those first principles and sort of ask yourself, can hx be zero? Okay, can the value of a network be zero? And can the value of a network at this point be zero? And it seems that you have got it. So yeah, uh, great. So again, coming back to what we are solving, zooming out, um, we are solving something called the degradation problem, and this is because it becomes more and more difficult for the network to learn identity mappings, which are ideal mappings for the first few layers of the deep network. So deep residual learning can help to solve the degradation problem. Okay, and that's in an essence what is happening here. The next part of the solution, so first part of the solution was deep residual learning. The next part of the solution is identity mapping by shortcuts, and the authors present residual learning building block which consists of two parts. So the residual function is the first part, which is uh, you know f of x and fwi, which is a stack of layers that learns residual between the input x and the desired output. This we already know. The the next part is the shortcut connection. The shortcut connection, so the residual part is the part highlighted here. Okay, this is what you all mentioned, hx minus x or fx, and this is what we are trying to learn. The other part is the shortcut connection, which is this u like line which is being added uh, to the next junction. And this shortcut connection is important because it allows the residual learning uh, building block to learn identity mappings. Okay, now I want you all to sort of put on your thinking caps and pause for a moment and think as if you are writing this paper. Okay, you have created this block. Where does the pointer go? You have created this block, and this block is what you're saying, that I'm trying to learn the gap between the desired output and the input. Well and good, you're trying to learn the gap, and that gap is a network of these layers, and you're trying to learn or approximate the function which is being contained in this highlighted part. Great. Okay, but you also need to add this shortcut connection. Okay, what would you make that shortcut connection be? Okay, will it be just the original information? Will it be an inverse of that original information? Will you be thinking like, okay, at this point I might have uh, I might need better features at this point because we are progressing deeper into the network, so let me add a layer in this connection and make it extract more features on the way. Will you think like that? Because there can be no right answers to this problem, right? This is really a problem where there can be n number of right answers, but will it really work? And that is where the ingenuity of the authors come into picture. That is where the authors really shine out, to me at least. They just simply said, okay, we don't need to over optimize at this point. We can just have this this shortcut connection be x. We can just pass this original x at this junction and then learn the residual. Okay, and that is why this is called an identity mapping, because it simply returns the input. And you know uh, identity mapping is a great way to preserve the information that might get lost while you propagate through layers. So uh, the authors, they are great mathematicians, they are deep learning researchers. They could have given n number of optimizations within this shortcut connection. But they had the foresight to see that, if I optimize at this junction as well, it will probably hurt the layers. So they just put an identity mapping, and that identity mapping is what helped the layer learn better. So finally, let's look at the architecture. And this is where my presentation will sort of fail. But when you revisit the paper, when you go, and I encourage all of you to go back and sort of read the paper again. Uh, One, to verify that I have not spoken absolute rubbish, and two, to kind of learn the residual between what I've taught and what you can extract from the paper, and that way probably you will learn better as well. So if you read the paper, you'll probably come across this diagram. And you'll be able to zoom in or squint better to understand it, because like I'm limited by technology, I cannot show you a more zoomed in version. The plane network is inspired by the philosophy of VGG nets. Of course, VGG is a topic for another video, but like it is a very famous family of models. It has convolutional layers, mostly with 3x3 filters, and follows two simple design rules. Uh, the residual network is based on that plane network. It inserts shortcut connections, like those skip connections that you saw, which turn the network into its counterpart residual version. And by doing that, one, you're able to learn much better, and two, you're also able to expand these deep learning architectures into depth, which has never been seen before. So in other words, or in plain English, you're able to make it more deeper, and by making it more deeper, you're also able to learn richer, better features through training. The code for this is actually pretty straightforward, which it should be given the simplicity of the residual block itself. I have kind of highlighted where the residual the part of residual is happening at this point. Since all of you were able to understand hx minus x pretty quickly, you'll probably understand what is happening here. Why you're adding x back to the network y. And like I will not discuss this code, because one, it's very simple, and two, it's pretty easily available on the internet. I think this was taken from the TensorFlow official uh, I think this was taken from the TensorFlow official guide or documentation. So I encourage all of you to go visit that, or whatever your coding style is. If you want to spin up a collab notebook and try to code this on your own, do it, because that will help you understand it better. But please do not take a screenshot of this, or do not try to copy it, because that will do you no good. So this is where like we are coming to the end of the stream, and we are trying to answer some like burning questions about ResNets. So ResNets came in 2015. Why is it still so relevant? Like, why hasn't there been another ingenious idea which has topped it? So in deep neural networks, the vanishing gradient problem can occur because you multiply many small numbers together, like when you calculate gradients during backpropagation, right? So because of chain rule, like du by dv can be broken down into like du by dx times dx by dy times dy by dv. And so if you multiply many small denominators together, you'll probably have like a huge, sorry, if you multiply too many denominators together, if you'll have a huge denominator, which will lead to a singularity, or something like your math breaking down. So that is where vanishing gradient problems occur. And those can occur in places like back propagation, and the result becomes even smaller. So the gradients that are too tiny doesn't help the network learn effectively. And this happens at deeper layers of the network, because, as I said, chain rule du by dv can be expanded into like um, all factorizable forms of u and v. So if all factorizable forms of u and v are actually all the subsequent, like, previous layers, then you might have a problem at say the 122nd layer, because you are essentially multiplying all the gradients, all the 121 gradients that you have encountered at this point. And that's when what you see on screen is going to happen. The gradients will essentially vanish. And if the gradients essentially vanish, what is happening is you have a loss. There is a certain loss function, but you are not able to understand that loss or approximate that loss, because you have no information about it. It has, like, it has been minimized to zero. So skip connections, also known as residual collections, helps address this problem by allowing information to skip certain layers. So you're essentially bypassing the multiplication steps that cause the gradients to vanish, right? And this is literally the best solution, because you're not going through that entire chain rule, but you're instead just adding plus k or plus x. We used to do this in calculus, where you we used to add plus epsilon, where epsilon is a very small number, so that we wouldn't have zero at the numerator or infinity at the denominator. So when you use skip connections, the activations in the deeper layer get some extra input from shallower layers, which prevent them from becoming exponentially small. And this is crucial, because when you're using activation functions like 10h, it can actually make the gradient problem worse, like the time we saw on the screen, where the gradient is kind of sinking low or exploding. So adding x or adding the information from the previous layer is actually preventing you from doing that, because it's no longer just simply a multiplication step, where the denominator might get unusually large, causing a vanishing gradient. It's also that plus x, which is going to prevent your chain rule from breaking down. So all great architecture, ResNet has evolved. ResNext is a natural extension of the original ResNet architecture. It introduces the concept of cardinality, number of parallel pathways. So instead of one residual network block, you have parallel residual network blocks. DenseNet, short for densely connected convolutional neural networks, where each layer receives the input from all preceding layers, not just one layer, all preceding layers, and this results in a highly interconnected network. There's also wide ResNet, WRN, which is a variant of ResNet where the width of the network, the number of channels or neurons, is increased while the depth is decreased. And you if you want to, you can probably search and find about these on the internet. And the adoption of residual connections has actually gone past cnn's, because many modern architectures and domains now use the concept of direct connection between layers, as I was telling in the first half of this stream. And the most notable one is transformers. I'm sure you all have heard of transformers. It's a popular architecture for natural language processing tasks. I don't need to say any more, but it also incorporates residual connections in their design. And each sublayer in a transformer, such as a self-attention or a feed, has stuff like feed-forward networks or and a residual connection on that. And it has actually been vital in training deep transformer models, uh, like GPTs. So augmix is again a data augmentation technique, but it blends multiple augmentation policies. And while it is not an architecture, it has residual based uh, architecture components inside it. And there's also auto-regressive models like some variants of transformers, or graph neural networks, which are designed to process structured data as graphs, and they also use residual functions to some extent. And all of this was just to give you a high level overview of like how relevant ResNets are at this point. So like if you are ever wondering, like, it came out in 2015, is it still like relevant? The answer is yes. And that's just some of the papers or some of the technologies that have used it. And now we come to the burning question: if ResNets are so great, if they are like the best possible thing in the in the deep learning world, why don't we sprinkle them everywhere? So every architecture is new, and every problem has to be solved in a different way. You can't just have a magic architecture and scale it to a billion parameters and expect it to solve everything. Of course, that's what happening into today's deep learning world, where you have uh, certain models which are scaled to billions and trillions of parameters, and you're expecting it to be conscious and bring you a cup of coffee the next day. But that's really not how serious research should be done. So coming back to the question of why not add residual networks or residual connections everywhere. So nested function classes, which is seen here, have a higher probability of containing the optimal function. But it is only and only if the network is deep enough. Okay. If you cannot expect a shallow network, like you cannot expect F1 bar and F2 bar to actually approximate the optimal function F star. Why? Because that means your architecture is not deep enough. And if it's not deep enough, or if it doesn't have many more layers, then what's the point? Because you're not doing what needs to be done to approximate the optimal function. Then the second is residual learning is beneficial when the residual gives the network a higher advantage than optimizing the parameters efficiently, which means that if you can tune w and b in that equation, wx and b, it will probably allow you to approximate f star. you know what I'm saying is, imagine you're at f4 bar, and you're at this end of the sphere, and you have probably tried like tuning 10 to 12 different weights and biases, and you say that, okay, and you have probably explored till this part, and you're saying, okay, I do not get enough returns, and I'll probably need to add one more function class f5 bar, and then see if I'm trying to approximate. No, that's not the right approach, because you need to explore f4 bar in its entirety to discover that f star or the optimal function is located here. What that means is that you have to first tune your weights and biases, you have to first tune your parameters to see whether you need deeper function classes or residual blocks in the first place. Because if your network is already being able to approximate the function just by tuning the weights and biases, why would you scale your model to greater depths? And then there's another problem, which is adding too many shortcuts will force the network to learn X much better than the features it might discover, which means you're overfitting. What that means is that if after every layer you're actually you're actually adding a skip connection, what is essentially happening is that your network is never being able to extract features from the original image. Imagine that game of telephone where if you have that skip connection, or if you are passing the original message after every one friend, what is actually happening is that the last person will just tell you the puzzle. They will not tell you the answer to that puzzle, or they will not be able to decode it, because all of it, none of your friends have had the chance to decode the puzzle or decrypt it. They have just heard the original puzzle, and that's what they're relaying back. And what this means is that you have learned the puzzle really well, you have memorized it, but you have not actually solved it. And in deep learning world, this is something called overfitting. So those are some of the things that we kind of need to tussle with when we want to add, when we want to sprinkle residual blocks everywhere. But again, um, also keeping these in mind might make you a better deep learning researcher, or a better deep learning engineer, because you are essentially tackling um, fundamental level problems. You're tackling how the network will learn. Do I need to add more uh, layers? Should I just tune my parameters better? And these questions are always good to ask at any point of your deep learning journey. And that was it. I don't have anything more to say on this. Of course, if you go ahead and read the paper, you'll able to extract much more. But that was essentially it. And now, if you have any questions, feedback, anything you would like to share, now's the time. And I would like invite Rishiraj back on stage.
Hi everyone. So I hope this session was super useful, and there are a couple of swags that would be distributed if you answer some questions that Ritik Raha might ask now. So, uh, do you have any questions that you'd like to ask the audience in order to distribute swags?
Um, let's see. Okay, let's see. Just a second. Can you remove my screen? Yeah, thank you. So here it goes. Name one, modern architecture that has used residual blocks. The first person gets the swag. If no one answers, then I get the swag. Is it possible to put it on the on the screen? Name one modern DL architecture that uses residual blocks. Repan Roy gets the swag. LLM is not the architecture. LLM is a class of models. But yeah, Repan Roy answered it correctly. It is transformers. So yes, he gets the swag, but like all the logistics will be handled by Rishraj. Do I ask more questions, Rishraj?
Yes, you can move ahead with one more question.
Okay, one more question. Cool. S- So the original residual network um, is based on which architecture?
Are there options that we would like to give for the audience?
If I give the options, I'll be able to guess it. But yeah, sure. You know, image classification. You're talking about the task. I'm asking about the name of the architecture, but I'll just put the options in the private chat.
Okay, so I have the options with me now. Let's see if anyone answers, or I will disclose the options. Then you can choose one
Sojal, you
from
are
them.
on the right track. Convolutional neural network, but there's a particular name to it. Like there's a name to the architecture. It's very like you have heard of it. If you have been in this session, I've mentioned it. Come on, residual network is ResNet. ResNet cannot be the architecture that it is based on. It is the architecture. It has to be based on a previous version. So what is that previous version? Like what is the original architecture which it is based upon?
So I guess I will disclose the options now.
Sure.
So the options are, I will display it on the screen. You can choose one from this, and let's see if you're right.
Yeah, I think Diksha got it right. It is VGG. Uh, uh, so she gets next swag. Sorry, guys, but yeah, none. Why would I ask a question and then have the answer as none? Wouldn't that be just cruel to everyone? But yeah, VGGNet is the right answer. So I'm not going to ask any more questions. Instead, if you have any questions for me, you know, in general, like I'm here for another couple of minutes, even in general, like pertaining to ML research or paper reading or how to read a paper, how to skim through a paper, all of those stuff. I'm just here for like some more minutes and shoot. I am not able to text, but Rishiraj has very kindly put my Twitter on wherever. I'm more active on Twitter, which is now X. But yes, right. So I think that's it. There are no more questions. I'm really thankful for everyone to be joining in on a Sunday morning to listen to me talk about a paper that came back in 2015. Um, Okay, now there's questions. How to understand a particular set of mathematics in a paper which you don't have a clue about? Shaptoshi, that's a really great question, and that's something that even most senior people find it difficult to answer. The answer to this is that when you find something which you don't have a clue about, when you find mathematics in a paper which you don't have a clue about, the first thing that you want to do is discover the larger set of mathematics that it's related to. So uh, like for example, if you're reading a paper and you come across something called topology, or topological models, that the first thing to do is go through videos or go through online articles that give you a high level view of what topology is. And then from there onwards, what you need to do is find the niche, or find the subset of topics that are related to the paper or the papers you're trying to read. Okay. So for example, if you're trying to read uh, you know um, Markov models or something like that, uh, starting with discrete mathematics, probability, all those things will help you. I will not give you a generic answer like go ahead and read linear algebra and go ahead and read statistics and probability, and that will solve everything for you in machine learning world, because let's be real, that is not the case anymore. But when you encounter mathematical formulas that you don't have a clue about, you can always take a picture, or you can crop that part and put it into a bard or chat gpt and ask it about it. It will give you a high level overview of what kind of mathematics it is. And then from there onwards, you can select those topics, go on YouTube, start reading about it. If you are really thinking about research and you have a mind to that, then I would suggest getting a handbook of mathematics or a guidebook of graduate mathematics would really help you, because then you'll be able to know that okay, this topic belongs to this superset. I hope that answers your question. Diksha asks, quite hard to find internships in AI ML as an undergrad. I'm contributing to open source. Any tips for this? This is really a question for people who want to go into the industry, but I'll try to answer it the best way I can. The the way to think about this is that your open source contributions is your portfolio. You have to have that portfolio speak to someone or something. And you can't be contributing to anything and everything and like expecting something from that. If you want to go into a particular company, if they have some open source or repositories, try contributing there. If there doesn't exist those open source repositories for those companies, what you can do is uh, try to create minimal examples of those technologies that you want to work with in you as your own repositories, and talking about that. uh, sh- Building in public and writing or sharing knowledge of what you have learned in public will always get you returns. They might not get you immediate returns like having an interview or sort, but they will always get you returns, and you will eventually land up in a position that you want to go to. So yeah, I think that covers it.
Okay. So we'll not take any more questions now. You can always ping Ritwik Raha on Twitter or just ask him any questions in his WhatsApp. He's available in most Google groups, as you might know. So we'll end this session here today. Those who answered correctly and deserve swags, they can come to our monthly offline meetups, one that will happen next month as well. So we'll distribute the swags over there. And also, please feel free to reach us out if you have any more suggestions regarding how we can improve this online ML paper reading clubs. And I hope you enjoyed this session today. So goodbye.
Thank, Goodbye. Thank you.